Hey Royals, lesson 6.2 on geometric sequences opens up with this, actually a couple of, well, one riddle and the one pay it forward example. Let's talk about the riddle here. It says, in the woods there is a cabin. I might try to draw this one out for you. In the woods there is a cabin, and in the cabin there are two tables, and on each table there are two boxes, and inside each box there are two bags. Notice I'm not that interested in what the type of thing is. Looks like I'm interested in the number of things. Inside each bag there are two snow globes. Running out of space here. In fact, you know what? I think I see the limitation of the diagram here. Let me try to get a sequence instead. So the first number of things, let me let T sub n represent the number of items. Not total, but just at a specific level. And then the index here is going to be a little bit trickier. The input is I don't really have a row number, but we have what is called like this pattern that has the fancy word here is iterations or just stages. Let's say let T sub n represent the number of items at stage n. Notice that n has to be an element of the natural numbers here. There is no stage 0, and there's no stages between stage 1 and stage 2. At stage 2, I'm talking about tables. At stage 3, I'm talking about boxes. So my sequence in this case, my first term, which is still going to be A, is 1. And then my second term is 2. That doubles to 4. Let's see. There's 4 boxes in total, and then 8 bags in total, and 16 snow globes in total, and then 32 cabins down here, the answer to the riddle. You can actually take it in two ways. One answer is you need to count this cabin plus that cabin, and that's where you get the answer 33. The other answer is, well, what happens when you look inside each one of these 32 cabins? Do you see two tables inside each one of those 32 cabins? Does it just keep on going on and on and on like that? Look up fractals or what was that movie that did this? I guess the ending of pretty much any well, the first three Men in Black did the same sort of thing. I don't know about the most recent one. Anyways, Pay It Forward is another interesting movie. I'm not sure if it's worth your time mathematically, but if you like that kid who can see dead people, then go ahead. Oh, shoot, spoilers. Never mind. That's a different movie, but anyways. Okay, so the answer of 33, sorry, doesn't really interest us too much. It's modeling this as a sequence. And notice that there's no common difference anymore. I'm going up by 1, then up by 2, then up by 4, then up by 8. I don't have a way of modeling my difference changing. What there is a common ratio. If I do term 2 divided by term 1, I get 2 divided by 1, which is 2. If I do term 3 divided by term 2, that's 4 divided by 2, which is 2. Usually, just be very careful in lesson 6.3, but usually if you find a pattern between 2, you don't need to show this pattern to be true for every single other. You can, you don't need to use 3 and 2 and 2 and 1 either. We could have shown that there's a common ratio here. So we call this a common ratio if the ratio of any future value to some present value is equal to the future value to some previous value, which is equal to some R value, we say the sequence is geometric. That's a weird use of the word, you might think, but arithmetic is related to adding. Our idea of having to multiply is intimately related to us finding areas. So the idea of multiplication was born out of geometric applications. Okay. What's next? Oh, yeah, our general formula. So you've got some first term, and then the next term is going to be a factor of r multiplied by a, not necessarily larger, because we'll see that r could be fractional or negative as well. the next term is going to have another factor of r. It's going to be a times r times r. So a times r times r. And the next term will be the previous term multiplied by r. Okay, let's define this in a way that might be useful in 6.3. In this sequence, any future term is the previous term multiplied by r, and that's why the number of factors of r increases by 1 each time. This formula right here is called recursive. We'll talk about that in 6.3. And I don't find it that useful because if you ask me how many items are on stage 7, I would need to know how many items are on stage 6. That means I would need to know how many items are on stage 5. I want to be able to jump all the way forward instead of having to go back and do all of that work. So notice that the first term has 0 factors of r. It has r to the exponent 0, which is 1. Notice that the second term has 1 factor of r. The fourth term has 3 factors of r. This means that the nth term of a geometric sequence is going to have n minus 1 factors of r. Compare this to an exponential function in the format a times b to the exponent x, and you'll just see a couple of differences. Well, one is that our common ratio can be negative, and we avoided negative bases very, very carefully. In this function, usually x was an element of the real numbers. It was a continuous function. Over here, this is going to be a discrete function, and is an element to the natural numbers. And then there's this little index shift here. Maybe this represents I'm starting at 100% integrity. So after 0 photocopies, there's 100% intensity or integrity. But here I'm starting with the first stage. So 1 is my first input here. 0 isn't really my first input here, but it's usually the first input that we substitute in. So there is your geometric sequence formula. Notice again, it should be easy enough for you to generate, so that when you use this in calculus, it's okay if you just forget what the formula is. All you need to do is know how to build it. I'm going to let you try out a couple of the examples on your own. Notice that you will be solving an exponential equation here, so there is a little bit of trial and error to find a common base, but you shouldn't be using trial and error to answer the problems. Let's look at the system example. It says that in a geometric sequence, the third term is 18 and the seventh term is 1,458. We're asked to find t sub 10. Again, I would say on a quiz or a test, maybe even using a system, either as a hint or as a direction, that I don't want you to just pull out a calculator and start typing away at this and try to guess and figure out what t sub 10 is. Most students who do that only get one of the answers. What? Okay, we are dealing with a geometric sequence. So we have a formula that we just built. We can use this formula that has 1, 2, 3, 4 different parameters in it. Two parameters, 2 variables. We have 2 clues though. Now be very careful. You can't treat this in a linear way. This is where you can't just do this minus that over that minus that. It's not a line. We're talking about a curve here. Okay. I'm going to substitute this information in. 18 is going to equal whatever the first term is multiplied by whatever the common ratio is to the exponent 3 minus 1. Again, just show that to your readers so they can figure out where you're getting 18 equals AR squared from. And 1,458 has to equal A times R to the exponent 7 minus 1. Notice my choice of using brackets here, and then I didn't use them here. Might be a good idea to have them, especially when your base is negative. Okay. All right, now with my grade 10 students, I usually try to show them how to solve nonlinear systems. And this isn't really a linear system, although we'll be solving it using a couple of linear skills. Let's get a focus here. Yeah, no, it's just my handwriting. Yeah, so yesterday, or sorry, in the last lesson on 6.2, when we had to eliminate a and a was being added, we eliminated by performing the inverse of that operation, which was a subtraction of the equations. Here, a is a factor of each one of these equations. A is being multiplied. So to eliminate a, you are allowed to do equation 2 minus equation 1, but it's probably not going to do what you want it to do. AR to the exponent 6 minus AR squared, the a's aren't going to cancel. I'm going to eliminate a by doing equation 2 divided by equation 1. I didn't show the operation on 6.1 with the subtraction. Maybe I should show the operation here for the division. Sometimes students just sort of memorize elimination without really thinking about what's going on. If this left side equals that right side and this left side equals that right side, then a left side divided by a left side will equal a right side divided by a right side, as long as this right side isn't equal to 0. Okay, it maintains equilibrium. Let's do the left-hand side now. I suppose I will use a calculator here. 1458 divided by 18. I don't know my 18 times tables all the way up to 81. And what's going to happen on the right-hand side? A divided by A, those are factors that eliminate. That's factored form. It still factors all the way back from the start of Unit 1. And then I have 2 factors of r squared that are being divided out of 6 factors of r squared. That leaves me with 4 factors of, or sorry, 6 factors of r, leaving me with 4 factors of r. Okay. Now, let's be very careful here. This is kind of like a quadratic equation. It's a quadratic equation if you see it as r squared squared equals 81. And then you could solve by factoring as a difference of squares. You've got r squared minus 9 times r squared plus 9 equals 0. R squared plus 9 will never equal 0. That has no roots. So you're going to have a solution when r minus 3 or r plus 3 is equal to 0. Most students don't want to have to solve this like a quadratic. Most students just want to undo the exponent of 4. The problem is that we can't really rely on our sketches because we don't have as much experience with what y equals x to the exponent 4 looks like. Maybe you should pull up Desmos and take a look there. Maybe I can convince you that in the past, when we have undone eventh roots, we have had to consider both the positive and negative solutions for inequalities that had to go on the variable side, but we were always able to rearrange it to the other side. The fourth root of 81 is the square root of the square root of 81. You can kind of see it here. You take the square root of 81, and then you take the square root of the square root of 81. Or you're asking yourself, what number, when multiplied, or sorry, when listed with 4 factors, will equal 81? Well, couldn't r equal 3 or negative 3? There are lots of situations in quadratics where we dismissed a negative solution. This is not one of them. Okay. Let me finish up the question, then I'll illustrate how this can happen. This means that what was I asked to find? The 10th term? Yeah, the 10th term. T sub 10 is going to be, oh, sorry, I need my a value. Let's substitute this into, actually, let's split it up into 2 cases. Let's put r equals 3 into equation 1, and we'll get 18 equals a times 3 squared. That'll be 18 equals 9a. That means that a would be positive 2 for the first term. Let's put this into equation 1. We would get 18 equals a multiplied by negative 3 squared. Watch what happens when I square negative 3. Oh, it's positive 9. So I get the same first term either way. But that's because the first term is an odd term, just like the third term and the 7th term are odd terms. We're asked to find the 10th term. This is an alternating sequence. We won't know if the 10th term is, or sorry, this could be an alternating sequence. We don't know if the 10th term is positive or negative. T sub 10 in this case is going to be 2 times 3 to the exponent 10 minus 1. Little bit of calculator work here. 3 to the exponent 9 times 2. 10th term could be 39,366. Or the 10th term could be 2 multiplied by negative 3 to the exponent 10 minus 1. Now, 10 minus 1 is 9. 9 is an odd exponent. Negative 3 to the exponent 9 is going to be negative 3 to the exponent 9, negative 19,683. When I double that, I get negative 39,366. Okay. We're still working with quadratics. We're still working with multiple solutions. We'll still run into trouble if we depend on our calculator too much. Our calculator will not give us all the answers that we need in our math careers. Let me show you what's happening here, but I don't want you to use this approach to try to solve the problem. Just want to, you know what? Let me just grab another piece of paper. Here we go. So, term 1, 2, 3. Here's 18. 4, 5, 6, 7. Here's 1,458. 8, 9, 10. So we figured out that the first term is definitely 2. And then if we just calculated the fourth root and we would think that the common ratio is 3, then this would be 6. So we're doing times 3 times 3. Let's speed this up. That's 54 times 3. 162 times 3, 486. And then you could do 4374. See, this is not this is not a solution. I am not showing what I'm doing or presenting a well-organized solution. I'm not using the skills that we've developed to get these numbers. But notice which values were given at the start. We were told term 3 and we were told term 7 right there. And then we figured out term 1. But couldn't it also be alternating? Couldn't it go 2 and then I multiply by negative 3 and get negative 6 and then multiply by negative 3 and get positive 18 and then get negative 54, positive 162, negative 486, positive 1458, negative 4374, positive 13122, and then negative 39366. Alternating sequences are really interesting. They can be super useful. They jump from positives to negatives when you're multiplying by a negative common ratio. But they're really easy to miss if we depend on our calculator a little bit too much. So once again, think about drawing curves, think about solving quadratics in a more appropriate method, think about understanding how many solutions an equation will have instead of trying to remember these things.